Study area characterization. The Corbera catchment is located in the headwater of the Mero Basin, at about 30 kilometers from the city of A Coruña in NW Spain, Figure 1. The catchment covers an area of 16 square kilometers. Elevations range from 65 to 470 meters ASL, with a mean slope of 19%. The geological substrate is dominated by the basic schist of the Ordonez complex, and the main soil types present in the catchment are umbrasol and cambisol, which represent 74 and 25%, respectively. Predominating land use is a forest covering 65% of the catchment area, followed by pasture, 26%, impervious areas, 5%, and cultivated land, 4%. The population density in the catchment is low, 35 inhabitants km-2, there are no industries, and human activities are reduced to rural traditional agriculture and livestock, 0.29 Luha-1. Location of the study area, general view of the Corbera catchment and land use map. The mean annual temperature is about 13 degrees Celsius, with mean annual minimum and maximum temperatures of 8.6, February, and 18.4 degrees Celsius, July, respectively. The mean annual rainfall is about 1,170 mm, more than 65% occurring between October and March. The annual mean flow rate is 0.18 cubic meters s1, and it is mainly supplied by groundwater. For more information of the study area, see Rodriguez Blanco et al. Methodology. The SWOT model was developed by the Agricultural Research Service of the U.S. Department of Agriculture, USDA, to quantify and predict the impact of agricultural management practices on water, sediment and agricultural chemical in large complex catchments, although it has been satisfactorily applied in small catchments all over the world. It is a continuous, distributed model, although not completely distributed, since it does not use cells but divides the basin into sub-basins that are further divided into hydrological response units, HRUs. For this reason, sometimes it is defined as semi-distributed. It is based on physical principles to describe the relationship between the input and output variables. It needs specific data from the catchment, climate, physical properties of the soil, topography, vegetation, soil management practice, etc., which are used to model physical processes related to the movement of water and sediments, growth of crops and nutrient cycles. SWOT simulations can be separated into two components, the land phase for water and pollutants loadings to channels and the routing phase for in-stream water quantity and quality. Regarding nitrogen, the model simulates in-transport and transformation at HRU scale, considering the processes of denitrification, volatilization and organic N, stable organic N associated with humic substances and fresh organic N associated with the crop residues are distinguished. Nitrate can be transported from land to stream network via surface runoff, lateral flow and groundwater flow. A more detailed description of the SWOT model can be found in. Research into the impact of climate in the future has focused on evaluating the effects that change in temperature, rainfall and CO2 concentration might cause on nitrate load, following the methodology used in. Two simulation sets were used, one evaluated the response of the catchment to changes in single climate variables, temperature, rainfall or CO2 concentrations, and the other one assessed the impact caused by simultaneous changes in temperature, rainfall or CO2 concentrations. In total, 14 different climate change scenarios were used, Table 1. Climate change scenarios used in the simulations. Notes: Scenario 1, T plus mean 2031 to 2060 C, Scenario 2, T plus max 2031 to 2060 C, Scenario 3, T plus mean 2069 to 2098 C, Scenario 4, T plus max 2069 to 2098 C, Scenario 5, P, mean 2031 to 2060%, Scenario 6, P, max 2031 to 2060%, Scenario 7, P, mean 2069 to 2098%, Scenario 8, P, max 2069 to 2098%, Scenario 9, 1.5 times CO2, Scenario 10, 2 times CO2, Scenario 11, Scenario 1 plus Scenario 5 plus Scenario 9, Scenario 12, Scenario 2 plus Scenario 6 plus Scenario 10, Scenario 13, Scenario 3 plus Scenario 7 plus Scenario 9, and Scenario 14, Scenario 4 plus Scenario 8 plus Scenario 10. The different climatic scenarios used in this study are based on predicted future alterations from regional models in the Ensembles project, Socioeconomic A1B scenario, for the closest meteorological station of the study area, for the periods 2031 to 2060 and 2069 to 2098. Due to variability of projections of future temperature and rainfall among the different models, Figure 2, the data from the models were combined to obtain the mean and maximum monthly rainfall and temperature for two periods, 2031 to 2060, intermediate future, and 2069 to 2098, distant future. Differences between projected and current values for the reference period, 1981 to 2010, were used to develop the climate scenarios. Variation range of forecast mean annual temperature and rainfall, Ensembles project, 4, A, period 2031 to 2060 and, B, period 2069 to 2098. Symbols identify different global models. The stochastic weather generator has proven to be a useful tool for generating climate data series of high spatial and temporal resolutions to be used in climate change impact studies. In this study, the GSCN weather generator included in the SWOT model was used to produce 30 years of synthetic daily weather data series for each climate change scenario, following the methodology used in. These weather data were used to run the SWOT model to simulate nitrate load under different climate change scenarios. The nitrate load yields under the selected scenarios were compared with the 30-year simulation of the reference period. T-tests were conducted to determine the significance of the difference in nitrate load between the reference scenario and the climate change scenarios. All of the statistical tests were performed in PASW Statistics 18 for the Windows Program Package, SPSS Incorporated, at a significance level of 0.05.